data structures and algorithms. So the one you see here tells you that there's going to be a 2. I'm told that a 2 is an elective, especially for those in IT. That's how the new changes brought it. But it is encouraged that if you want to have dominance in the field, it's going to help you build up yourself. So that is just something to let you know. Uh, uh, if you want to really doing your implementations or your designs, so if we should take it from some of the examples Bida was giving us regarding preparing this or preparing that, you know that most of the things that you prepare, they can take time. Okay, they can take time. So then sometimes you look for means or ways to make sure that the cooking you are going to do, you do not waste more time. So you find other means to get it done on time. Okay, so time is very important. Then there's another thing. When you are cooking, depending on the size of the family or the people you are cooking for, you may want to look at the kind of bowl you are going to use, the space available for you. Okay, so that if you know you are cooking for a family of 5, family of 3, family of 10, a group of people of 18, you do not expect to use the same space. Okay, you're not going to use the same space to do the same cooking. So then it means that you have to always think about space and then time it will take for that food to complete. Okay, sometimes if it's going to take so much time, it also depends that you put under the pot, right? So if it is a gas cooker or gas cylinder and you tune it to the very lowest part, of course, you expect it to boil at a certain gradual rate. Similarly, if you put it at a very high rate, you also expect that it's too high. You expect that you bring it to a certain level that you can achieve. So when we look at algorithm efficiency and analysis, all we are trying to do is that we have an algorithm. The algorithm, for example, is going to process a certain task. But the way we have written it, either when it gets chance to go into memory, you remember when we were doing 207, memory was very, very important to us. Okay, so the architecture, the memory was very essential. Why? Because every execution takes place in memory. And memory itself, we cannot simply go and flood it, because when memory is full, nothing else can work on the computer. Okay, when your memory is full, everything ends because it needs space to work, it needs space to run. So memory, once memory is gone, there is no computer. That's the reality. Everything will come to a standstill. So then we need to manage memory such that this code is not going to occupy so much space. It's going to hold on to the processes. Other algorithms, other tasks that needs to also be executing cannot, because this application or this algorithm is holding on to the space. And that is the essence of trying to understand the efficiency of an algorithm. Now, moving on, we say that if you look at analyzing algorithms, especially before you code, I know most of you, those few of you who are able to write some codes or develop some applications, you would always want to begin coding. You start your coding. Some of you do not even plan what you are doing. You just code out of something. But before you code, you must always analyze your algorithms. Before you code, you must always write an algorithm. Okay, you do not just code in computing. It's a very bad plan or process to code without writing an algorithm. Okay, there should always be an algorithm, because the algorithm is going to help you shape exactly what to do. It's going to let you know how to scale, because the program or the code you are putting together is going to receive input And you saw it when we were in 204. We give input to the system, how the inputs get into memory, right? And then with all the other memory components, all the other processor components, how those things are processed and then given back to the output windows. So you would want to always ask yourself, what input am I giving to my algorithm, and how will it scale? How will it grow with the given input? With the given input. So we want to understand efficiency analysis as a machine independent way to compare algorithms. So at every point in time, we are given a problem. Okay. So we are given a problem, and that's one thing you must always understand, that when I have a problem, so my basic problem is I want to cook rice. Okay. I want to cook rice. That's my basic problem. And to be able to cook that rice, I have to know my input, in this terms, the quantity of rice, right? So that's my input. So what quantity am I going to do with? Then operations, what am I going to do? So maybe I'll need salt, I'll need oil. People cook rice with oil, people cook rice with salt, they need water. All this could be operations in the other side. In the reality of programming, this is going to be all your arithmetic and logic operators. Okay. So my plus operations, my subtraction operation, multiplication operation, all of them are there. Then how is the thing is going to run? So a runtime model. Then the growth, you know that when I put rice of a certain quantity, by the time you finish cooking, it has grown to a certain level. So you expect a certain growth. You gauge, you know that, okay, I'm going to cook for 5 people. I want everybody to have 2 spoons of the rice. So how much input of rice do I put to get that 2 spoons at the end of the day? You need to be able to have that, and that's input. Then you have to make your design decisions as well, which is very, very important in this regard. So your design decision is as important as it is. So the question will be that, what will happen when the input becomes like 10 times, okay, or when the input should grow to 100 times, when the input even becoming 1,000 times or even larger? What happens to your application? What happens to your system? Okay, when the input is growing, when it's expanding, when it's scaling, okay, when we are having more students. So I did a system and I used what do you call it? Microsoft, uh, what do you call it? The Microsoft database. Eh? Not the MS SQL, the Access database itself. So I use Access database. And Access database, when the number of people grow, when it becomes larger, immediately it may crash because it cannot accommodate a certain size. So then you have to know, by design, you need to go in for maybe MS SQL database or Oracle database or MySQL database or whatever, Sybase, Postgres, whatever it is, so that as the thing is growing, the input is growing, you are able to accommodate, and then you're able to move on in that order. So understand the focus in here. So at least everybody should know what an input size is, which is very important, and identify it correctly for any computational problem that we have. Then know the primitive operations, know what we call runtime from memory use, and the total space for auxiliary space. Then you should know the best case, the average case, also the worst case analysis. And then, as when we are doing searching and other things, then the notations. Today we'll be looking at just big O notation, but as we move along, we'll put together and understand the other notations as well. So why do we need to know these notations? We'll try to understand what we call the asymptotic analysis. Okay, why it matters, and we can make some progress. So this is a workflow for determining the efficiency of an algorithm, or analyzing the efficiency of these algorithms. You first have to specify the problem, okay? Then you choose your input size. Then you identify the basic operations. You count the number of operations, and then you simplify the growth, how to grow. So the problem clarity is that what input is valid, and then what output is required. So you know that it is only I feel that when you start doing anything, okay, or in most endeavors, you need to know your output before you even begin doing anything. Okay, so you need to know what your expected output. What am I expecting? You need to know your output before you even move on. Okay, because if you don't know what you're looking for, you cannot even get there. So then you need to also understand the cost model. The cost here is that which operation will best represent the work. And then when it grows, begins starting growing, when n is becoming larger, what happens? Okay, so when the input is becoming large, and like I indicated in the previous slide here, the inputs can be growing. You can have 1,000 students, 2,000 students. Now, UG, for example, we have about 70,000 students. So imagine we have our systems, and our systems cannot scale. Okay, it cannot grow, it cannot accommodate students. Then you cannot access the resources. But because we have a system that, based on as the input size grows, we're able to scale up, and that's why we're able to accommodate students to any number. We can, with our current systems that we have, we can accommodate up to about 100,000 even students. Okay, just that we don't have enough classroom space, we don't have enough faculty, and that is why we are always regulated how many we can bring in. But if we had enough faculty, we have enough classrooms, we have, we can accommodate, the systems can accommodate over about 100,000 plus at every given time, and that is a better way of thinking. Now, when we say input size, okay, we are looking at that variable that derives the cost. That variable that derives the cost. So it is a measure of how large the problem instance is. When we say input size, the variable that drives the cost, measuring how large the problem instance is. So the same algorithm that you write can be efficient if you have small input sizes. Okay, but the moment you increase the input, it becomes impracticable. Okay, and that is some of the things. So an algorithm that you write can work better today because the input sizes are small. But the moment you scale up, it crashes. Okay, the moment you scale up, it crashes. And that is it. So if I have a problem like I'm searching for a list of items, then input size n will be the number of items. And then the typical output will be an index or not found. So when I'm searching, so I have an array of elements here. So and then index 0, index 1, 2, 3, and I have A here, B there, C here, 8 there, 9, E, 10, 2. So these are elements I have in my array. So array ARR. Okay. So this is what is in ARR. So the search simply means that if I'm searching for any item, the number of items will be the number of items in this list, which is here 8. Okay, because I'm starting at 0, so it is n minus 1, which is 8. So the last element here is n minus 1, because the number of elements here is n, and n is equal to 8. But because I start at index 0, the last element is always n minus 1. Accra, call this K. For Kumasi, call this T. For Tamale, I can also go to Tamale. Now from Kumasi, I can go to Cape Coast and come back to Accra. So I have Cape Coast here. So it's a map, okay? So this is a path. So a path, this one I put the 2 lines on it. They are all paths, okay? So I can follow these paths and go to where I'm going to. And then I can know the distance from one end to another end. So we know the distance from Accra to Tamale, okay? We can know that. And that is how we look for routes in a map. So these are nodes, and then the connections route, and to enable you to plan adequately and effectively. We can compare strings as well. So the length of strings we can match. So I can have a VIDA. Okay, so VIDA is a string here. And if I want to know the length of elements in this string VIDA, I can tell using to string convert, and then it can tell me 4 elements, and I can also determine all these things in there. Now let's try this in class activity. I'll just some 3-5 minutes, and then you tell me your answer. It's 5 minutes. Once you are done, raise your hand and you share what you think with us. Are you there?
Yes, sir.
If we talk and you don't talk back, it's a two-way communication. So we know you exist. 3 minutes more. Hello.
Hello, sir.
Please, can I talk about B? I want to talk about B.
But we are
Yeah.
not. We are finished before we come to B.
Hello, sir.
Yes.
Okay, please, I'll speak of A. So, for the student ID in an unsettled list, for the input size, there should be the number of student IDs in the provided list.
Mm-hmm.
So, for example, maybe
Go ahead. We are not hearing you anymore.
hello, sir.
Yes, we're not hearing you.
Oh, okay. So, I was saying that for the input size, it should be the number of students in the list.
Mm-hmm.
And then the operation that follows for this one should be a comparison between maybe every existing ID and then the student's ID that is being searched for. That tells whether they are present or not. So then the
Okay.
ID that we as compared to the existing ones.
Okay.
Yeah.
The next one, B.
Okay, so with the B, we can have the input size to be the number of marks of the students in the doing that course. And
Mm-hmm.
then the primitive operation could be the cumulative sum of each of the marks that we have written. Yeah.
Good. C. Yes, C.
Hello, sir.
Hello, sir.
Yes, go ahead.
Hello, sir.
Let's see.
All right.
So with the C, the input size, you find the number of intersections or landmarks with the courses, like with the points available, and then the number of paths connecting them on each of the campus maps. And then with the operations, after adding the distances of the points, you calculate the distance and then you find the shortest one in them.
Okay. D.
Hello, sir.
Sir, for
Yes,
D,
please.
hello, sir. So for D, you check the length of the DNA.
Mm-hmm.
That's for the input. So the length of the DNA. For the primitive, you check for the characteristics. Let's say you've checked two DNAs, their length, they are different. Then you check for the characteristics.
Okay. So with all these scenarios, you have to solve that what grows when the problem becomes larger. You have to ask yourself that question, and then that will help you to be a good designer. So this was what we were expecting, which most of you have already talked about it. So the input side depends on the representation and operation we need to analyze. That is what the input side expects from us. Now, what are primitive operations? We've been mentioning, and I've been mentioning primitive operations. So they are also a simple cost model. Okay, why am I saying that? Because they take a constant time under a chosen computational model. Example could be the assignment operator, the arithmetic operation, comparison, array access, function, return. All these are primitive operations. So we count how many times the chosen primitive operation execute as n grows. Okay, so as these ones are executing, as n is growing, we try to understand it from that perspective. So the exact time varies by machine. So depending on the machine, and the growth pattern is also a
Hear you.
moment.
No,
Sir,
sir.
please, you are
No,
not
sir.
audible.
No.
Okay, so we are looking at an example where we
Sir,
are
please,
summing up.
sir, you have moved forward. You were
Uh,
explaining
you have to go
time
back.
back a little bit.
A primitive.
Yes,
Here.
please, sir, you are here.
Oh,
You are
I
here.
have passed a long time. Oh.
No,
Then
sir.
you, please,
Please,
you
Sir,
are
no,
we're
we
asking
were
here.
questions.
here.
It means I was out of the meeting.
Yeah, you were on number two. You were explaining
Okay,
the examples.
good. So number two, I was saying that the primitive operations examples are the assignment. You know, assignment operation is the equal to. You know that when you have one equal to sign, that's assignment. When you have the double equal to, that's what equality. In computing. So if I say 8 is equal to 8, this is the equality. When I say that A or B is equal to 6, this is an assignment. Eh? So this is an assignment operation. This is a equality operation. So when we want to look at equal, we use a double equal to sign. When we want to assign, we use one equal to sign. Then we have the arithmetic operation. We have the comparison. So greater than, less than, greater than or equal to, less than or equal to. They are all comparisons, right? Then array access, like we did, array A at index, let's say 0. So I'm accessing the array. So array access function call, so return, we can say that return sum. It's a function call. So all these are things that are part of the primitive operations. And we can count how many times that these primitive operations, okay, the chosen primitive operations execute. And as they execute, n is also what? We look at them from how n is growing. And we said that the exact time varies by the machine. So depending on the requirements of the machine, some may have some i5 with a certain system requirement. Some may have an i7 with a certain system requirement. Some may run on a server with maybe 4 GPUs. Okay, so it means that based on the system requirement, certain the n groove, the groove pattern of n will be seen in the as a key thing in there. Then I said that in computing all this, we always refer to a function called T of n. So the function T of n is approximately equal to the a constant term C times the number of primitive operations plus the lower order cost. And I said we are going to use this function a lot as we move along, especially when we began looking at the asymptotic, okay, the asymptotic notation. So we'll try to understand a lot of these things there, where we look at the big O, okay, the big O, big theta, big omega, and then also big theta. As we discuss these notations, we'll understand how we can compute them using this. And that brought me to this example that if I want to sum an array For example, the algorithm sum array, okay, the function sum array takes two parameters, the array and then the number of the input size. So I was saying that anytime you are writing such algorithms and pseudocodes, you always bring your function name, then the input. What input are we expecting? So here we are expecting an array of a certain size. Then we are expecting the sum of all elements in the array. Then now we can bring the algorithm. So we say we assign sum to 0 to sum. Then for all I set to 0, I moving from what 0 to n minus 1, do this sum plus the array at I, because we store it back in sum. So here sum is 0, array at I is 0. So it's mean that what is in sum now is 0. Now the loop goes to 1. Okay, sum is now having 0, so it's 0. The array is now at 1. Okay, so 1. So sum is now having 1. Now I goes to 2. Sum I is here 2. 1, sum is holding 1. So 1 plus 2, now sum will hold 3. And that is how it works. And then at the end of the day, if I was 4, okay, by the time we go to I is 3, here is 3, here is holding 3. So 3 plus 3 is 6. So sum is holding 6 at this stage. When I goes to 4, I is 4, sum is holding 6. So 4 plus 6, sum is 10. So return what? 10. Sum will return 10 at this stage. And that is how it works. Are you following? So the input size n is the number of elements. The basic operation, we have one addition. This is one addition here. And then one loop, one iteration, a loop. So a loop is an iteration. Then the algorithm touches every exact element once. So it means that because we have n number of elements, the upper bound will be big O of n. More of this we explain as we go along, but that's the upper bound of things. So counting operations for summary, the sum, this assignment here, this sum 0 equal to this. I've told that it's the same as saying sum, okay, is equal to 0. And we are assigning it. So we assign 0 to sum. That operation is a constant operation. So the frequency of execution is 1. So it is a constant, it's contributing just constant. Now the loop is going to run from 0 to n minus 1, we are reducing. But if it's going to run on itself, it's going to run n plus 1 times, which is a linear contribution to it. Then the AI, which is the array at index I, sum plus that, putting it in sum, is going to run or iterate n times. Okay, n times. So we are going to have it also linear. Then the return, which is the component here, this one will also what? Contribute 1, because the constant time. So it will be 1. So if you observe here, I said that how we count how many times the chosen primitive operation executes. And that is what I'm doing here in this table. Okay, I'm counting them. How many times they're executing. This one is the loop is executing n plus 1 times. This calculation, the sum equals sum plus AI is going to execute n times. Then the return will always return 1, because it's constant. After the sum has been calculated, then it will return it. So in this case, what do? The function becomes a of n plus b of n plus 1 plus c. So all this 1, 1, 1 will be all added. So we'll have what? We'll have n. So we're going to have n times, okay, we'll have n plus 1, okay, plus then 1 plus the other one, okay, plus the other one. So this is an arithmetic. We'll get what? 2n, right? Plus what? 1, plus 3. So this growth is on this n. Okay, and because this is constant, we ignore the constant term. We ignore this constant term. Hence, this is going to grow at big O of n. That is how we calculate it. So we use this function that I said you're going to see a of n plus b n plus 1 plus a constant term, which is 1, 2, 1, 2. So then that arithmetic give us, let's say, n plus 1 plus 2, which is going to give us the same 2n plus 3. Then we'll get the constant terms are dropped. He says that when using big O notation, we keep the dominant term, okay? The dominant term in the growth, which is the n, and the rate and drop all constants. And that is why when we had 2n, okay, plus 3, we drop all the constant terms and leave the dominant n term where the growth is. Then we get what? Big O of n. Right? Good. Then, okay, so do this mini lab for me quickly. So analyze the number of comparisons made by this algorithm. Hurry up based on the explanation I've just provided you. 2 minutes. This one you don't have to take too much time. Done. If you have followed what I did, you should finish in just 2 minutes.
It's 3 times. So it would iterate over A and iterate over N. So to compare with the line if AI is less than threshold. So on the first iteration, the first argument there is A. So it will compare it if it is threshold. If it is not, it will move to N. Compare if it is not, then it will now move to threshold. And that will be 3 iterations. Thank you.
So what's the input side? I've not answered all the questions here.
Yeah, the input sides will be 3.
Hmm?
3.
How do you know it's 3?
The parameters for the function. We have
Nope.
A.
No,
Okay.
you didn't understand input size. Look at the definition of input size again.
I think the input size is n.
It's n.
Input size is n.
It can be
Yes.
the
So
Okay.
the
Okay.
input size will be the number of array elements, which is the n.
Which is the n here?
Yes, and then when you look at the times. Yes, so yeah, that is how it's going to be.
So here will be what? The growth will be what?
To be O of n.
Okay.
The group will be the number of operations grows linearly with input size, which is n.
Okay.
Sure.
Understand and follow this one. Because that is how you're going to analyze all your algorithms. Every time you begin working, you need to always analyze your algorithm before you code. So you have to know before you do any coding, you have to know what is happening, how your algorithm is going to be. You have to know. So this kind of analysis, we call it theoretical. We have 2 kinds of analysis that we do with algorithms. This is theoretical analysis. And then we are going to see another one that we would, when that we are writing the code, then we run with different input sizes, which we call that empirical. So these are the 2 forms. We'll see soon of analysis that we can do. Are we getting there?
We are following, sir.
Okay.
Yes, sir.
So this is the what I was just talking about. So when we have the mathematical model, what we just did, we count the operations, we ignore the hardware, the compiler, all those things are, and then we just try to see. So we use our model, what we just finished. But the empirical, okay, so when you write the code, that example I've given you, the assignment I've just given you, you see I have an SQL file with inputs and every other thing there. So when you run the code, you have to change the input sizes to see what is happening. And then you can go through that to know how the growth rate is. So take note of that. So usually if you have done that, you see that the growth rate will increase as the input sizes also increases. and then we can determine the various growth. So if it's a log time growth, this is how you see the growth. If it's a linear time, um, this is it. If it's a n log n, and then if it's a quadratic time, so depend on the growth and how things show, especially regarding the inputs that you get. So the notations here, if it's constant, we can assess array access the typical one is a constant. It does not grow with n. Okay. If it's logarithmic, the binary set, for example, why is it so? Because if I have a binary set, I need to always know the middle and then know the number I'm looking for, whether if it's less than the mid or it's greater than the mid. And then that will help me to discard one part of the set to be able to do that. And because with large cuts each step, it grows in log n. Then linear, if I'm scanning the list, one pass over input, that's the practical meaning. Then n log n, linear arithmetic or linear arithmetic. When we are doing merging sorting, merge sort, so we break the components into two. We sort here, we keep breaking. When we have sorted, then we can merge the outcomes of what we found here. We'll be looking at all of that. Then quadratic, comparing all pairs. So cost rises quickly, so it escalates most of the time. And then exponential, you try all subsets, usually infeasible in some instances. So these are common growth rates and other things that are there. Try this activity. You rank the following functions in terms of their growth rates based on the understanding we've had. Then which would you prefer for a system expected to handle 1 million inputs and why? Yes, analyze quickly and let's discuss.
That's the fastest. I
I'll,
think there's
sir,
something.
please, I'll prefer the login.
Don't worry. I know what I'm asking him. Let me finish.
Okay.
So if you have a different answer, I'll come to you. I just want to know what he has done and why, what his choices were.
Okay. I'll prefer
Oh, the same person
log
who gave me this.
yes n log n.
N log n.
Yes, sir.
Why? Well, he's still thinking. Next person. Who else have a different answer from what you did?
Sir,
Hello,
so
sir.
from
After that, I'll go with n, and I'll go with n log n. After that, I'll go with n square,
And then two.
and I'll end with the fastest to be 2 exponent n.
So which one do you prefer in your case to handle 1 million inputs?
So please, I'll prefer n.
This one?
Yes, please.
Why?
So because if I'm choosing n, because of scalability, that's why I'll choose n. Because if I'm trying to choose other factors like n square, it will become, or 2n, it will become expensive to computate. Such as if you are using 1 million input, n square will be like 1 billion operation, which could cost, which could take about hours. But and also with 2n, that will be impossible to complete. So with scalability, I'll go with the N, which with this modern computers, it will take a fraction of second to computate.
Okay. One more attempt, and then we move on.
But I want to clarify something. Now, if the fastest is 1, which is constant time, then why don't we choose that one?
I'll come to that.
All right, sure.
So it means you are agreeing with this answer, and
Yeah,
not this
that's.
answer.
No, I agree with the second one. If that starts with the fastest with 1, which is the constant. So if 1 is the fastest in this, then why don't we choose 1, which
But
is
the
the
thing is
constant
saying
time for the
that
fastest
move
possible?
from slowest to fastest. So from what you are saying, if you say you are aligned with this one is saying 1 is slowest.
No. 1 he said that from fastest to okay.
No, from
No,
slowest to
the
No,
I
person
from
fastest.
says
fastest.
from
From fastest
slowest
to
to
lowest.
fastest.
it's
Ah,
slowest to fastest.
then
So
we have
the
No,
to start
N
from
is
fastest
first
the
will
one.
be
fastest.
2 raised to the power n.
It's the fastest.
No, say from
From
slowest to the fastest. Now it must be the first one.
no. The fastest should be the 2 raised to the power n, because the question says we should arrange these functions from the slowest to the fastest growth as n becomes large. So he started by stating that 1 is the constant, which is the slowest,
Lowest.
followed by log n in that order.
It's only 1.
So how many of you agree it is this? Number 1.
No,
Let me see your hands up.
one.
I agree that 1 is the slowest.
Oh, just show your hand if you agree is number 1. I only see just one person. Okay, how many agree that it's number 2? A lot more. At least 8 now. 13, 12. Okay, 15 now. Good. So, those who think it's number 2, when we say something is slowest, what do you understand? And when it is fastest, what do you understand by that?
So hello,
Yes.
sir.
Yes.
Sir, please, to my understanding, when we say something is slowest,
Yeah.
it means that that thing will take a longer time for it to complete its action, or for it to give out a result. Then if something is fast, it means that it will take a short period for it to generate an outcome. So in that case, looking at the results for, I mean the question, the answer the guy gave, the second one he gave, he stated from the slowest, which is 1 being the constant, then log end, followed by what? End, in that order. So he stated accordingly from the slowest to the highest.
Okay, so the log linear or the linear becomes a bit better. Quadratic itself may be too slow for larger input. When you have so much large inputs, exponential also require more restrictions, and that is why this order becomes more possible if you have 1 million input sizes. So the constants matter for small inputs, okay? But when growth dominates, then it becomes a big deal. So take note of that.
Hello, sir.
Yes.
Please, I agree with your answer, but I still need a little explanation. My understanding is not clear.
What the, yeah.
Because I think if why don't we choose the fastest since the input is higher?
So when you say why don't we choose the fastest when the input is higher,
Yes, please.
So when you have more inputs and then you go and you are choosing the fastest, the question is that this is a constant time, so
Okay.
it has no bearing. You
Sure.
understand?
Yes,
Uh-huh.
please.
So because it's a constant time, it will not change anything.
Okay.
But the one that you see some change in usage of resources is when we know that the growth is occurring. So like we have 100,000, then 900,000, then 1 million. Okay.
Sure.
So depending on the growth, how things are changing, we're able to observe and see how resources are also being utilized. So that is simply the rationale behind uh, general algorithms and then the time and space is occupying. So remember at the beginning, I said the whole key, well, the two keywords here is time and space.
Yes, please.
Mhm. So as the input is growing, what time is affected, what space is affected. That's all the time what we have to be thinking of to
Okay.
inform us on what to do our decisions.
Sure.
Okay. So now we have another example. So I have nested loops. Nested loops means I have two loops. Okay. So this is the outer. The O here, the big O here is the outer loop. Okay. So the outer loop. And this one is the inner. The big I here means is the inner loop. Okay. So now, when you look at this algorithm, we are counting pairs. So once we are counting pairs, we still have an array and then the input size. So we assign 0 to count, and our first loop will run a certain number of times, and it's starting from 0 to n minus 1. Then the second loop begins from I plus 1, meaning that I is 0 here, right? So it means that when this one is starting at 0, this one is starting at what? J is starting at what?
1.
1. Then it also moves to n minus 1. Then we compare. So there's we check if we add if a of I plus a of j is equal to 0, then we can say count plus 1 and put it in count and return count. That's all we are doing. So the inner loop will run fewer times as I increases. Okay, then the total pair checks the n minus 1 plus n minus 2 plus it will keep going till we get to 1. So this sum equals, so we are going to have n into brackets n minus 1 all over 2. And when we work on this one, we are going to get n squared, okay, plus n times 1, right? So it will give us 2n, isn't it? Hmm?
Yeah.
N squared
Yes,
minus what?
minus n.
Minus, this should be minus, right?
N squared
Yes,
minus n.
N squared minus n
yeah, divided by 2.
over 2.
Over 2.
So now we just said that this is what the dominant term, right? So this is
Yes,
not a
sir.
dominant term. This is also not a dominant term. So in terms of growth rate, it will grow in the dominant term, and this is typical quadratic. So as we compare, comparison is powerful, but it's always growing in what quadratic fashion. So that it becomes expensive to compare. That's why when you have a lot of things to compare in programming, when you are looping and you are comparing, it takes more time or computational resources, okay, than the usual thing. So sometimes instead of comparing, there's a way to rewrite or optimize this code to minimize the amount of comparison so that you can make use of gain more memory and other resources as well. Now we move to best
Hello,
case,
sir.
worst case,
Sir,
yes,
sir, please,
and
can
average
you
case.
the the slice you just for this one. Yes, please take the count per side. That please again for me, please.
So we have this loop running from 0 to n minus 1. And this one is going to go to n minus. We keep adding up with all the terms that we have to add up, all the operations. So here we are summing all the operations like we did previously. Okay. But because we are doing this sum of equals, how do we know? We can find the n, all the evaluation that we do. Okay. So we get n of n minus 1 over 2. But it's because of these two loops here. Is when this one runs at 0 and the control gets to this one, it will run all the number of times of n. Okay. Then it will come back to this again. This will go to 1. It will run all the instances of n here until this one. If let's say n was 4 here, okay, at 0, and here n is, let's say, 5 here. At 0, all the 5 items will run. At 1, all the 5 items will run. Like that till this exits, and then this also exits. So the inner loop depends on the outer loop. Okay, that's what it's trying to do here when it comes to most of these loops. But when we get here, because we are checking, okay, a of I. So a of I is this array here, array of I, this first loop. So this first loop is coming to this guy, and then this second loop is coming to this guy. Okay, so when we check, we add and see and is equal to 0. Then we increase the counter by 1, and then we store it in count and return count. So this will be one operation. 1. This will be what? This adding. This also performing. So we will all of them added up gives us this, and then when we expand and evaluate, we get this n squared. So we always have to analyze this segment of code, like we in this table here. You must always analyze them this way and know the frequency of operations. Do you understand? Before you can
Yes.
add all of them to get the outcomes you have to get. Do you get it?
Hi, sir.
Yes, sir.
Yes.
Hello, sir.
Thank you.
Can you please retouch on the dominant term? Why n squared dominant term?
That's the one with more growth. When we say dominant term, that's where the growth is seen more. Because the growth will happen if n is increasing. Like if I have if n is 10, so here is 10 squared minus 10 over 2. So which one is growing bigger? 10 squared is growing bigger. Can 10 be bigger than 10 squared?
Not at all.
No.
So this is that would be the dominant term. So this will be the dominant term. This is where the growth is.
Sure.
Because if this is growing bigger, this will always be 10. This one will not change. But this is growing at a very quadratic way. You see it? That's why that is a dominant term. So then the growth is on that. And that's what we just write for the notations. So the case analysis, when you are doing when you're asked, you have to always check or what input makes the algorithm faster. Then what input makes it slowest? Then what happens under a defined probability model? This is the case analysis to be able to know whether it's a best case, an average case, or worst case. And the reason why we need to understand is that when worst case comes in, it supports reliability guarantees, okay? And then average case guide expected performance. And then best case alone can be misleading. So you do not always need a best case scenario, because sometimes you may think that once you have the best case, the algorithm is doing well. No, you must train or stress the algorithm in the worst case scenario. Okay, so in the worst case scenario, how would the algorithm perform? in the average case scenario, how will it perform? And then based on those stress testing you have performed, you can really vouch on the performance of the algorithm. But if you just follow best case all the time, it may be misleading. So the average case analysis must state its assumptions. Otherwise, it also may not be meaningful while you are doing that. So that's why all the time you have to look at the worst case. So worst case scenario, if the algorithm should have all these, what will happen? Now let's look at the linear search algorithm. So I have a bag. I'll put my things in there. I'm going to search for the items. Okay. I can search. I have my array. I have my number of elements. I have my key. That's a linear search. So linear search takes 3 parameters. So the input is always an array, and then the search key, and the output will either be an index key or it's not found. So if we run our loop, I starts from 0, I goes out to what, n minus 1. Then we check if a of I is equal to the key. If equal to, then we return the key I. That's the index. Remember? So this is a typical linear search, an array. Okay, an array. So we have the elements in here. So this is the, I always tell the index is what it is. So 0, 1, dot, 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 2, 3, 4, 5, 6, 6. So I have different things in there. It can be 2, it can be 3. Visualize them. I can't write everything. So imagine there are things in every location. Okay, and you are searching for an item. Let me just try and put some items here. You are searching for an item. So my key here is equal to 10. That's what I'm searching for from this array AR. Okay, and then the number of elements is how many? What's my n? N is what?
7.
7, sir. 7.
7.
Okay, 7. So then now I have it. I have my input. I have my key. So I now check at location I. So I'm looking for my key. My key is what? 10. So I is what? 2, right? Is 2 equal to my key? Is 2 equal to 7?
No, sir.
So
No, sir.
it will go what? It will
go
check.
not found.
So you
No.
have to write 2 equal to 10. By fitting 7.
Yeah, the key. Sorry.
Now searching.
The key is 10, yeah. So it will not finish here because the loop has not ended. So they're not found, no just come. You understand? Because there's
Yeah.
the first iteration. So the second iteration will come. So we'll move from here to 1. Then we'll see 3 there. Is 3 equal to 10? No.
No.
We'll move to 2. Okay. Is 4. What is that index? 2 is 4. Is 4 equal to 10? No. Is this 3? It will also be no.
No.
Is 8 equal to 10? It will say no. We'll go to 5. It will say no. We'll get to this one. It will say no.
Worst case
Okay,
scenario.
so worst case scenario is what we have just done. So at worst case scenario, we have searched for all the items, isn't it?
Yes,
and yet
sir.
we didn't find it. So it means that because this is linear, it's going to grow at O of what? Of n. Because I have to go through all the list of elements, yet didn't find what I'm looking for. So that's the worst case scenario. So when we say worst case, that's what we have to always be thinking of. So the input size is there, the print operation is what we are doing here, comparing no sorting is needed here, and we can stop early when the key is found. Okay, so once the key is found, we stop. If the key is not found, we keep moving through the list till we get there. And because the key is not in there, we have to go to the last end. So imagine that we have a linear search and the number of elements here, I'll not even see much, it's 100. And you have to go through how many times? Loop through how many times? 99 times, right? Which is because we are starting from 0. So 99 times, which are anyway 100 times. Before we can, and after going through all, it tells us the key is not even there. And imagine if the key is also at the 100th location. So this is index 100, okay? Which is the 99, or I start from 1. So let me call it 99 precum. Index 99, which is the 100th item. And this, I'm looking for 6, okay? So the key is 6. I'll have to go through 99 steps before I can see that the key is there, right? And that's the worst case. So that's how it works in this manner. But the best case is that my key is 2. Okay, my key is 2. So at the first search, A of 0 is equal to key, which is what? There, right? It's there. So A of 0, I get it. So once I find it, that's the best case. I found my key. Average case is I'm looking for 9. So after about 3 iterations, I get it there. Not the average case. So take note of all of these. And in this case, once I get my key here, it is O of 1. Okay, it's O of 1. That's all. I found the key just at the first stage. So this is a flow chart. You can go through it. And then this is an example trace. So later I tell you to trace. Yes.
Okay, so looking at the worst case scenario, knowing very well that your key cannot be found in the array, do you still have to prove?
But how will you know it is not there?
Once you look at the list, you automatically see that it's not inside.
No, because you see it's 5. What about if it is 1 million items? If you have lots of 1 million items, how will you know the key is there?
Once you have your list, you automatically see it. Once the list
You
is
can't
So
taken.
see
a
it
log of 1
automatically.
million
When
items, how will you see that this log you are looking for is not in the list?
you can't
You
see
You
it.
can't
can't
see.
unless you prove.
No, even if the logs are 100, how will you know that this log you are looking for is not in the list?
You go through it one by one.
In practical case, there's no way you can see that the thing is there or not until you have searched. Oh, I'm looking for a student in my class. Okay, I have your IDs. So there's a what do you call it? I'm going to input the grades. Now, most of the students sometimes can come to they can come to the class. Okay, maybe you try to resolution for grade input is you have let's say 150 students, but you have these 200 students. How will you know that this particular all the 150 IDs with the one you are just searching only to finish and tell it's not there? Because at the end of the day, you can't tell which of the students registered and dropped or which one didn't drop. So you need to search for the student. So there's no way you can tell me that you can observe. Yes, by observation, this small number, you can observe because it's a small number. But you still can't tell me that because you observe and it's a small number, it is. That's why if you look at what I have here, you are using a trace. So tracing means that by inspection, this is the thing. The key is what? 54. So by inspection, you know that my first item is there. So it's O of 1. Okay, now I'm going to look for a key. The key is 37. So after first iteration 1, iteration 2, iteration 3, iteration 4, I find my distance. So after 4 comparisons, I find it. So this is neither best case nor worst case. That's why it's the average case. Now I'm searching for 82. 82, I go to iteration 1, iteration 2, iteration 3, iteration 4, iteration 5, iteration 6, and it's not there. So that's the worst case scenario. And that's why we run it at big O of n. So by inspection, yes, 82 is not there. If it's not there, it means I'm going to, although it's not there, how did you know? Your eye search for all the list before you conclude it's not there. Right? You search for all the
Yes,
list.
sir.
You just wouldn't just say it's not there. How do you know it's not there? You still search, whether you use by inspection or by whatever algorithm or whatever, you have searched. Okay, the brain looked at it and saw that it's not there. The searching process took place. And you have scanned all the list of elements before you can conclude that 82 is not there. You have searched all of them. So it's not about I can search and that is all. If I have a large number of students, Eugene, my class, a class of let's say 650. On Sakai, they are 700. You are going to enter their grades, they are not 700. It means there are some 50 students who are not in Sakai. How do you get to fish out these 50 students? You need to search for them. You need to search for them. Otherwise, you can't find them.
Hello, sir.
Yes.
Sir, please, I want to ask a question. The question 2, why is it that we didn't write big O of 4? With the
How do you
first
write big
write
O
big
of
O.
4? We can
I
write.
want
Have
to
you seen
ask
me writing big O of a certain number before? It's always in terms of n. So the
N.
first one,
And
which
you
is a
wrote
constant
1.
term, because the constant term is 1, that's why it's always big O of 1. But apart from the constant term, the average case could be the n over the number of elements, which is n over the average, which is average is always the number of the size of the element, right? So if I'm finding the average of, let's say, 5 numbers, I'll have to add all of them and divide by 5, right?
Yes, please.
Yes, sir.
And then, so this is the same trace. Okay, you are tracing to see. So normally when you are tracing, you can build a table like this. I'll show an example of table to build, but you always can trace the number of processes that you go through to know how you can find this, the number of comparisons that you need to do it. So how many comparisons do you need to do this? It's a simple work.
Sir, for the number one, it's one comparison, then you get the 9.
Mm-hmm.
And the 25 is 4.
The 25 is 4.
25 is 5
It's
comparisons.
5. The 25 is
The
5
25 is
comparison.
5, it's not 4.
3, 4, 5. Okay, it's
It's
5.
5.
Mm-hmm.
Yes. And then
And
the
then the
50, you are going to
50
be doing
is
7.
7
7
comparisons.
comparison.
So how would you classify the best or worst case time here?
So the first one is the best case.
The
The
best
middle one
case and
goes.
the rest.
The worst case is
The
the
rest.
The worst is the
50 having
50.
Worst case
7.
is 50.
Okay. So
And then the
because
average one is the
9,
middle
you
one.
did one comparison. So this is like a trace, okay? Your search key, your comparison, your keys, all the time look at it. So the comparison was 1, and that's the best case. 25 was the middle, so middle search. And then the 50 was 7, which was the worst case not found. So that's the best case is O of 1. Worst case is O of n. And like I said, the average case, because you are finding the average, okay, that's what you do. And it's also still giving you O of n because it's still be within n will be the dominant term. So take note of that. So same for binary search, okay. We find I always tell we also always have to find the mid, and then we use the floor low or high, and then we can see if it is the mid plus 1 is low or mid minus 1 is high, then we can return any of those ones. So you can also look at that as well, and we can do a trace of that. And then there's a mini lab here in Java. You try to work on it before the next class. Memory use or space complexity. Yep. So the rest are, I think, some few cases and mini labs that you need to do, which is not difficult to handle. So the rest are just mini labs I put in there to help you understand. So go over them, try your hands on the mini labs, go to the textbook itself. I'll make some reference to the textbooks. Okay, so there are 2 textbooks in there, the Levante and then the other algorithms book. Try and solve questions on them. Okay, on your own, look at it and solve some questions. But I'll point you to some of the questions as assignment, and then you solve them as well for me. It is only practice that will get you to understand most of these things. So solve them, get to understand how to solve these. When you have a function and you have to determine the running time, you have an algorithm. Look at a lot. Just try your hands as many as you can. I will share some assignment activities for you. So I think let me see if I can find one of them. Let me just show you the efficiency and all those things. So go through all of them. So like some of these things here, okay, this is what I want you to be doing. Some exercises like this one. Give an example of something that requires algorithm content at whatever. Try your hands on these kind of exercises. It will help you. Then the chapter, you go to the next one. So this is where we are looking at the sorting and insertion stuff. So you try to look at some of the things in there. Then the exercises. So at every end of these things, there are exercises. So you try as much as you can. Look at the algorithms, the order of growth. So like for example, express this function n cube 1,000 plus n square over that in terms of big theta. So theta is average case. That's a tight bound. Then you try your hands on most of these ones. So design algorithms, divide and conquer. There are different things we are going to be exposing ourselves to. So look at all of them and solve more problems here. Now the next book is this one, designing algorithms, Leventy. So with this book as well, go over each of them so you can see the foundations, fundamental analysis of algorithms. So measuring the input. This is what, in fact, this is the primary book I normally use, including the other one as well. So with this as well, what is an algorithm? All those kind of things are here. This includes, as you saw it in the material, the middle school procedure that you saw. Then do some few examples here. Then fundamentals of algorithm problem solving, understanding it. So the techniques for doing that. You know what it means. Understand what we are doing. Algorithms are here. All the various the Cn, the T of n components, this table showing the various growth analysis, the best case scenario and other things. So it will have here for each of the following algorithms indicate the natural size metrics for all the inputs, the basic operation, whether the operation count can be different from the inputs or whatever. So computing a sum of numbers, as you saw, factorial. Hands on each as we can. So we have one here. These are machines and how to find order of growth plus solve all of them. Okay, you can see a number of things are here. Try your hands on these. The theta, we'll do the notations next week. The theta, the omega, all of them. You see them coming up. It's the materials are already loaded for you. So the asymptotic notations, they are there. If you go to the destination, that's a lesson lecture 3 and then lecture 3E. They are looking at this especially. So go through those and solve most of the problems in here. I think that is the only way you can understand and experience this carefully. And look at how all the time algorithms are written. All the time how the pseudocodes are written. Look at all of them and then build up your competencies in that respect. I hope it is clear enough. If you don't spend time on the books,
Yes, sir.
you will be weakened.
Yes, sir.
Please
Yes, sir. Yes,
read
sir.
the book, solve the problems, and then you should be fine. This is very, very, very important. Okay, the Levante book, for example, is necessary. You have all these here, so solve every recurrence equation, and you determine everything in there. Solve them. Try your hands, and then I will send an assignment myself that this chapter answer question A, B, C, or whatever. But until I give you, solve the problems on your own. Now, the assignment I've given you, the one that is called the activity pack, that one is going to begin building you on the programming. Okay, we are using Java to do this work. So if you look at it, I have Java framework already. Study the code in there carefully. Okay, try to understand the structure. You've done Java already, but this is the time also for you to now on your own begin looking at it. So pipe yourself very well into that and then get to follow through the work. We'll discuss the outcomes next week. So some of you will share your screen to show me what you've been able to do from that work and what you also on your own were able to do from the books. See you next week.